So if we are, so we'll say for the 0 to the 0, 1 to the infinity, or infinity to the 0 form, the answer is use logarithms. That turns out to be the one-line answer. This is actually going to be super important for us. So I'd like to walk through a couple of examples here so that you can see what I mean. The most common example of utilizing this is the following. Suppose we want to take the limit of x goes to infinity of 1 plus 1 over x to the x. You may recognize this. If you don't, you'll find the answer surprising. This, as it stands, is of the form what? When x goes to infinity, 1 over x goes to 0. And so this is of the form 0 to the infinity. This goes to 0, this goes to 1. So this is of the form 1 to the infinity, which is one of our indeterminate forms. So that's a problem. So how do we turn this into something that we can use L'Hopital's on? That is 0 over 0 or infinity over infinity. It turns out we need to rip down this power x, and the way to do that in a controlled way is through the use of logarithms. Now, here's a parenthetical fact that we need to import. Note, the exponential and the logarithm are inverses of one another. So that means e to the ln of x is just x, and the natural log of e to the x is just x. So what I'm going to do is I'm going to rewrite this limit as the limit as x goes to infinity of e to the ln of 1 plus 1 over x to the x. I'm using this rule, where x is this entire limit. Another rule to remember is the power rule, which says that the logarithm of something to a power, I can take this power and I can move it down front. I can take this power and I can move it down front here. At the same time, the exponential is a continuous function, so this limit can move upstairs as well. And this is equal to e to the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. Now this limit is the interesting one, because this limit is of what form? Infinity times 1 plus 1 over 0, that's ln of 1. The natural log of 1 is 0. Well, wouldn't you know it, we've already handled this case. What happens when we have a product of, say, 0 times infinity? We do this quotienting business. So what I'm going to do is I'm going to take this x and I'm going to move it downstairs as a 1 over x. So we're going to get e to the limit as x goes to infinity of the natural log of 1 plus 1 over x over 1 over x. And now we see that this limit is of the form 0 over 0. That is really good because that means L'Hopital's works. So now we can use L'Hopital's rule to rewrite this as e to the limit as x goes to infinity of what? The derivative of the upstairs becomes the derivative of the natural log is 1 over whatever was inside. And then the chain rule kicks in. We differentiate by whatever's inside, and I'm going to get negative 1 over x squared. And then the denominator becomes the derivative of 1 over x, which is negative 1 over x squared. these two items cancel. And so I'm left with now e to the limit as x goes to infinity of 1 over 1 plus 1 over x. And now this limit's well understood. 1 over x here is going to go to a 0, and so the net result is this is e to the 1, which is just e. So indeed, this limit is equal to e at the end of the day. This is the most common use of L'Hopital's rule within the context of Calc 2 and sequences in Calc 2. So let's take a look at what we were looking at in class and see if we can't use this knowledge in order to understand what was happening there. So what I'm going to do is I'm going to pull up here the handout from the in-class portion. And you'll notice that above this is about where we ended earlier, right? These are the objects that use the squeeze theorem. And what we have here is something we need to use L'Hopital's rule to discuss the convergence or divergence of. And the reason here is because right off the bat, if you take a look at, say, the limit as n goes to infinity of a sub n, we get the limit as n goes to infinity of ln of n over n, which is going to be infinity over infinity. That is bad. But that means we can use L'Hopital's. So that means we need L'Hopital's rule. However, L'Hopital's rule utilizes derivatives. We cannot take the derivative of a sequence. A sequence is a bunch of points. We cannot take the derivative of just a bunch of points in a row. We need something smooth enough to actually compute the derivative of. What we need is the continuous interpolant. So this is how I want you to structure these answers. We are going to let f of x equal ln of x over x be the continuous interpolant for a sub n. Now we are going to look at the limit as x goes to infinity of f of x. The important observation here is that the theorem that we talked about in class tells us that this is equal to the limit as n goes to infinity of a sub n. But within the context of the f of x function, this becomes the limit as x goes to infinity of the ln of x over x, which by L'Hopital's rule, so again, I'm signaling to the reader what I'm doing, this is going to be equal to the limit as x goes to infinity of 1 over x over 1, which is going to be, in this case, just a 0. So it turns out that this limit is actually equal to 0. But in order to make it work, we had to pass to the continuous interpolant and then use L'Hopital's rule. The situation does get a little bit more complicated. For example, here we have another sequence, b sub n. Notice, parenthetically, that if I wanted to compute the limit as n goes to infinity of b sub n, this would be the limit as n goes to infinity of, say, n plus 1 over n minus 1 to the n. I would get, on the inside, I would get a 1, and upstairs in the exponent, I would get an infinity. Well, that's a problem, because that's an indeterminate form. So what that means is that we need L'Hopital's rule. And in this case, since it's of the power form, indeterminate form, which is this form, not now, which is this form right here, we might call this the power form. We know we need to use logarithms. So again, I'm going to use this trick, this e to the ln trick, and we're going to see how we can use it. But before I use that trick, since I want to use L'Hopital's, like beforehand, I need to pass to a continuous interpolant. So here, I'm going to let f of x equal to x plus 1 over x minus 1 to the x be the continuous interpolant for b sub n. Now the theorem says that the limit as n goes to infinity of b sub n is equal to the limit as x goes to infinity of f of x, which in this case is the limit as x tends to infinity of x plus 1 over x minus 1 to the x. Using the e to the ln trick, this is the same as the limit as x tends to infinity of e to the ln of whatever the function was, x plus 1 over x minus 1 to the x. And as we saw last time, the power rule of logarithms kicks in. This is going to come downstairs, as well as the continuity of the exponential pushes the limit upstairs as well. So therefore, this is going to be equal to e to the limit as x goes to infinity of x times the natural log of x plus 1 over x minus 1, where now this limit is of the form, well, ln of 1 is equal to 0, so this is of the form infinity times 0, which, as we saw in the previous slide, this again puts us back in the infinity times 0 case, the product indeterminate form, which requires us to do one of these quotient tricks. So the quotient trick we're going to use is very similar to the last example. This will be e to the limit as x approaches infinity of the natural log of x plus 1 over x minus 1 all over 1 over x. Where now this limit up here is equal to 0 over 0 form, which means it's L'Hopital time. So this is equal to, by L'Hopital's rule, e to the limit as x goes to infinity of what? The numerator will become 1 over the inside, but 1 over a fraction is just its reciprocal, x minus 1 over x plus 1 times the derivative of the inside. The derivative of that requires a quotient rule. So actually, how about we move that down here so I can write that out in full detail. This is going to require a quotient rule. We're going to get low d high. The derivative of x plus 1 is just a 1. Minus high d low, again just a 1, all over low squared. And that's just the derivative of the top in the L'Hopital rule. Now we need to divide by the derivative of the bottom, which is of course negative 1 over x squared. So simplifying this, we get e to the limit as x approaches infinity of what? Notice that one of these x plus 1s will cancel with one of those x minus 1s. Upstairs, we're going to get x minus 1 minus x minus 1. So that means we're going to get a negative 2 upstairs over an x plus 1 times x minus 1, all over negative 1 over x squared, which we can clean this up significantly. This will be e to the limit as x approaches infinity of negative 2x squared over x plus 1, x minus 1. And this is a limit we can barehandedly compute. We're going to get, since the degree of the top and the bottom are the same, this limit's going to be equal to a negative 2. So this is equal to e to the negative 2, otherwise known as 1 over e squared. So apparently, that is the limit of b sub n. Limit of b sub n is equal to this item at the end of the day. I am fully aware that there are a lot of moving parts here, and I really encourage you to rewatch this more than a few times, pay special attention to each step, and carefully write it out. Now, we do want to speed up our ability to do some of these limits, so there are some commonly used limits in this class. And that might be stuff like this. The limit of ln of n over n is equal to 0. We saw that on the previous page. The limit of the nth root of n is a 1. The limit of the nth root of anything positive is also a 1. The limit of x to the n, where x is less than 1, is a 0. And here's that formulation we saw on the previous document. If this x was equal to a 1, we would have gotten e to the 1. But in general, if that's just an x, we get e to the x. And then here's x to the n over n factorial. You are allowed to know these, and you're allowed to internalize these. However, you should endeavor to go through and practice proving these yourself as well, just so that you can understand sort of the inner workings. But for example, when we do a problem in the future and we need to know, oh, the nth root of n, what is that limit? We are just going to import the fact that it's equal to a 1. So these are things I encourage you and invite you to commit to memory. That said, in order to continue calculating limits quickly, we're going to want to say things like, for example, when we look at that limit, what we want to say is that the growth rate of n exceeds the growth rate of ln of n. Because if we think about this sort of picture right here, what I want you to start thinking about is I want you to think about this quotient as some sort of a competition. Right? Because as we take the limit as n goes to infinity of the ln of n over n, this is going to infinity over infinity. So they're both blowing up. Right? This is a L'Hopital problem. But the fact that the actual answer is 0 means that somehow the denominator is going to infinity faster than the numerator. That is, the growth rate of the denominator, that's what this is, the denominator, exceeds the growth rate of the numerator. What this means is that we can start putting together a growth chart where one function, like in this case n, grows faster than another function, like ln, if the limit of their quotient is equal to 0. And that's the next object we're going to introduce. we're going to talk about growth rates. So I'm going to take the conversation back to f of x land. So our goal is to compare, so we're going to say this. We're going to say, we say a function f grows much faster than g if the limit as x goes to infinity of f of x over g of x is infinite, or equivalently, if the limit as x goes to infinity of g of x over f of x is 0. Because what that means, if f is growing faster than g, that means that when you look at this quotient, the numerator is winning out. So therefore, the overall quotient is actually following the numerator, and we get infinity. Or equivalently, if we were to swap this quotient, we'd say that f grows much faster than g if, looking at g over f, again, f is winning over g. So therefore, the overall behavior of this fraction is similar to what happens when the denominator goes to infinity first, and something like 1 over infinity is a 0. We notate this by f less than, got this backwards. We notate this by g is less than f. So f is growing much faster than g. It is possible for f and g to have similar growth rates. So we say f and g have comparable growth if, thinking back to, for example, the limit comparison test, if the limit as x goes to infinity of f of x over g of x is not 0 or infinity, but it's some number, say m, which is not quite 0 but not quite infinity. So the question is, what can we do with this information? Well, in sequence world, we can define the exact same things, because this is true for the continuous interpolants. In sequence world, the following is true. We're going to let P, Q, and A be positive numbers with A being greater than 1. It turns out that there's sort of an ordered growth chain. It turns out that the ln of x, n, to the p is somehow super slow. It's outpaced by n to the q for any q, which is outpaced by a to the n, which is outpaced by n factorial, which is outpaced by n to the n. So the reason this is useful, for example, is as follows. If I wanted to, for example, consider the sequence a sub n equaled n factorial over n to the n, and I wanted to know what the limit as n goes to infinity of n factorial over n to the n is, well, if I remember that n factorial is here and n to the n is here, that means n to the n grows much faster than n factorial, which means the numerator is beating out the denominator, which means this limit is equal to infinity. Similarly, if I took something like the limit as n goes to infinity of, say, 2 to the n, and then up here we have ln of n to the power of 1400. Despite 1400 being really, really big, notice here that in this case, we're looking at a to the n, where a is 2, and ln to the p, where p is 1400. And regardless of these numbers being so different, eventually the growth of the exponential will far outpace the growth of the natural log. So in this case, we find that the answer is going to be 0. Because the denominator is higher on the growth chart than the numerator. And so this gives us access to a lot of really, really, really fast ways of computing limits. And you are 100% encouraged to use these facts on your homework. Now, sometimes this won't get you too far. For example, when we saw this problem doesn't really fit any growth rates. So we have to do it the long way. But look back at these items. We see here that this item, and number 6, follows from a growth rate. We see that the first item follows from a growth rate. And so these growth rates are really, really useful, and I highly encourage you to use them. But when you use them, you're going to want to somehow inform me, oh yeah, I'm using the fact that the first item is dominated by the second item, or something like that.